it wasn't understood what was basically the cause of, what were the mobile charges which were inside a conductor. So there were two kind of experiments which really helped us in understanding what those charges are and what kind of nature do they have. One most common experiment was the Hall measurement experiment. So in this case what you have is, for example, if you have a conductor in which you want to know what kind of mobile charges you have in a conductor. So what you do is you connect it to a certain potential by certain conductor, and you want to see what you have for this piece of metal is that its dimensions are well known. So the length, the height and the width, they are well known. So you apply a potential to it, you have an ammeter which measures the current. So when you apply this, what you have is you have a current which flows through it, because you have a parallel electric field which is established because of the potential, and that field would be V naught by L, which is the potential divided by the distance. So that's good. But what people do is also apply a magnetic field as well, and that magnetic field is perpendicular to this face, so which is in this direction. So if you have perpendicular field, if you have a magnetic field which is perpendicular to a certain velocity, so if you consider, let's say the charges which are inside a conductor are positive charges. So if they are positive charges, so this would be the direction of those charges in that case. If that's the velocity, you have a magnetic field which is coming out of the board, what would be the direction of the force on it? So that would be V cross B, so you would have those charges, they would accumulate, or they would be forced down. So what you would have is a net accumulation of positive charges inside here. So overall this was neutral, but you have this extra charges which appear. So what you would have, you have an extra field which appears inside a conductor. So what you have is, you have an extra field which is a perpendicular field which appears because of those accumulated charges. And in which direction you had the magnetic force? It was downwards. So the magnetic force was a downward force. So as more and more charges accumulate, so the force due to the electric field which is downward, and the force due to the magnetic field which is magnetic force downward है, electric force आपके, so what you have is an electric field, और इस electric field अगर create हुआ है, उसको force किस direction में होएगा? Positive charges के ऊपर वो upward आएगा. So both these forces would cancel out at a certain point, and at that instant आपके पास क्या होएगी? जो आपके पास electric field है इस direction में, उसकी force और जो magnetic field की force है इस direction में, both of them would be equal. So that would be the case. And if that's the case, then the electric field at that position is given by the velocity, जो कि इस direction में थी of those particles, multiplied by the magnetic field. And from here you can find the velocity, which would be the drift velocity at which those charges were moving in that direction. So this is equal to, you have the field. If you know the distance between these two faces, you would know कि potential इसके across जो develop हुआ है वो क्या है आपके पास. So that would be that potential difference divided by the distance between these two faces, divided by B. What if you do is, if you take this face and you take this face, and then you connect a voltmeter with it, so that this one gives you a positive and this is connected to the negative terminal of the volt battery. So this face is connected to a positive terminal and the lower face is connected to a negative terminal. So what you would record is a certain voltage, and that voltage is called as Hall voltage. So that's the voltage. So if I replace del V by Vh, that's the Hall voltage which you would measure अगर वो charges यहाँ पे accumulate होते हैं. ठीक? So what you get is basically the velocity of those charges जो कि enter हो रहे थे. So अब the question is, you know this Vh because this is what you are measuring. You know B क्योंकि आपने B field में establish करा है, this you already know, and you know D, which is the size of this length. ठीक है? H है, sorry, it's not D because h would be the distance between the two faces. ठीक? अब from J equals to E and V, that's, if I multiply by A, then I get current, so that would be the current which I have. So if I multiply by the area, that would be the current I have. So from here I can write that V is equal to current divided by E and into A. So I can replace it here. So what I would get is I divided by E and A. This equals to VH by D or by H into B, and if I rearrange it, I would get E and A VH equals to I HD, from where I can write that N is equal to I HB divided by E A VH. So what you get is the number of charges which you have inside the conductor, and those are the mobile charges. Now the question is whether those charges are positive or whether those charges are negative. How would you find it? So let's say if I had a positive charge, this is what I would have. I would have a plus charge on this side, so what I would get is a potential VH. मेरे पास वैल्यू क्या आएगी VH की? Would it be a positive VH or would it be a negative VH? I would measure a negative VH because ये minus जो है I have connected it to this one and plus I have connected to a minus one, so that's an inverted situation. अब the question is, let's say if those charges जो अंदर move कर रहे हैं वो negative charges हैं, what would you see? You would see that those negative charges would be moving opposite to this electric field जो कि यहाँ पे है, ठीक है? So this would be the velocity of those charges. अब इनके ऊपर magnetic force किस direction में लगेगी आपके पास? So you have V and you have B. So V cross B is upward, but because the charge is negative, it would be downward. So you would have such a situation. अब यहाँ पे आपके पास इलेक्ट्रिक फील्ड किस डायरेक्शन में होगी? So the electric field would be downward. अब अगर आप पोटेंशियल मेजर करोगे, Hall potential across this, so that again you have a positive here and a negative here. What would you measure? Would you measure a positive potential or would you measure a negative potential? You would measure a positive potential. So because negative is connected to a negative side and positive connected to the positive side. So the sign of the Hall voltage, which is VH, it would give you कि अंदर जो charge carrier है, whether they are जो mobile charges, whether they are positive charges or whether they are negative charges. And this would give you how many mobile charges you have there inside. So it is given by the current, which you are already measuring by the ammeter. You have height, which the height of the sample you already know. You know the magnetic field, you know the charge on the single carrier. You have the area, which is the cross-sectional area, and the Hall voltage which you are measuring. So all of these things are known. So you would immediately know कि अंदर आपके पास mobile charges कौन से हैं और किस sign कौन सी sign है. So that was one of the first measurement which was done to determine the size of the charge, the type of the charge, and the amount of charge, mobile charge present. So any question here? Then the next experiment was done was a slightly different experiment. So let's say if you have a metal, so in metal you have mobile charges and you have charges which are static. So static charges are those which are at their own places. They are heavier one, they are not moving, but then you have these mobile charges. What if you suddenly apply a force on the whole metal and give it a certain acceleration in that direction? अब ये mobile charges जो हैं, they are moving around, and the only thing which is keeping them inside are these surfaces, because they can't go out of those surfaces. The electrons need some energy to go out of the surface. See? But they are free to move around in the solid, but these things, they are not free to move. The question at that time was whether those mobile charges were positive or whether they were negative. People didn't understand it. of time. So what they did was like, they accelerated this. What if you accelerate such a thing? What would happen? What do you think? So if you are moving this, those heavier masses, they would move with it. But because you have a gas inside, the gas would slightly lag behind because it is free to move and you are pushing the whole thing in this forward direction. So what you would have a net accumulation of negative charges on this side and a net positive charge which would appear on this side. So if you have a voltmeter and you measure the voltage, the sign of the voltage would tell you कि इस साइड पे आपके पास पॉजिटिव चार्ज अपेयर हुआ है कि नेगेटिव चार्ज अपेयर हुआ है. So that's how kind of the experiment was done initially to. So you apply a voltage to it. So you just accelerate it. If you accelerate it, because this gas is free flowing, so and it is bounded by this barrier. So the whole, if you move this, these are massive particles which form this whole body. They would move forward, but the gas would stick to some part of the gas would stick to this side of the surface. The net negative charge would appear here, and a net positive charge would appear here. So if you measure the potential, the sign of the potential would give you. So if it would be a, अगर मोबाइल चार्ज अगर पॉजिटिव होती तो इस साइड का पॉजिटिव साइन अपीयर होता है and so on. So that's how people did those measurements. So yes. No, this is just you take any conductor, it would have electrons, and those electrons are free to move. So you can make an idealization or assumption that the charges, they are free to move, so they are just like a gas within a container. So that's an assumption which you make. So let's try to do a slightly different experiment than this one while moving this conducting body. What if I have a conducting bar like this and I give it a certain velocity in this direction with a certain velocity v bar? But the difference between this case and that case is that you do it while there is a magnetic field present inside a magnetic field, such that the magnetic field is out of the board. So you have a B field which is out of the board, and you move a conducting bar with a certain length across it. So that's the length. So what do you expect? Of course you would have something like, so initially let's say you have a constant velocity. You may, so if you start with a zero velocity, you would accelerate it first to this constant velocity. If you accelerate it, you might have a negative charges which appear on this side. But once they accumulate on this side, they would also move with the same velocity as you are moving the bar with. So you have those negative charges which are moving with a velocity v bar in this direction, inside the bar. So the velocity with which you are moving the bar, the negative charges also move with the same velocity because they are sticking to this edge of the conductor. So you have a moving charge which are negative, and those charges, and those are mobile charges. The positive charge which appear on the other side, they can't move. They are not mobile charges because they are part of the heavy atom. So अगर ये charge move कर सकते हैं, those charges are within a magnetic field. What would they experience? They would experience a certain force. And what would be the direction of that force? So if you have V in this direction and V is in this direction, so the V cross B is in downward direction, but because the force is on an electron, so you have that force in the upward direction. So the force which appears due to the magnetic field on the charges is in upward direction, on the negative charges. So if you have that force, what would happen to those electrons? They would start flowing in that direction because that's where the magnetic force on it. And what would happen if you do it for some time, that you would have a net accumulation of negative charges on this surface and a net positive charge on this surface. on that edge of it. True? So if that's the case, what you would have is a magnetic, so you would have an electric field which would form inside, and that electric field would be from positive side to negative side. Yes. What would be the direction of the force because of this electric field? On the mobile charges, it would be, on the mobile charges, that force would be in the downward direction, because the mobile charges are electrons and not positive ions. But the magnetic force on those mobile charges are in upward direction. True? So let's say initially you start moving, so you have some charges which appear, and you have a small electric field which accumulate, and because of the small electric field you have a small electric field. But as you move it further, more and more charges would appear on it, and at one time it would happen that the electric force and the magnetic force, they would exactly balance out each other. So what would happen after that is that you would have a fixed number of negative and positive charges here, but overall they won't change afterwards because there would be no net flow of charges afterwards. So you have this kind of equilibration between the two forces, and once that occurs, you have a net potential drop across these two. So you would have a net potential which would be given by the potential on the positive side minus the potential on the negative side, and that would, so if you have the electric field divided by L, where L is the length, that would give you the electric field as well, which you form inside a conductor. So what you have done, so what if you increase the velocity in that direction? So velocity, if you increase the velocity of the bar, what would happen to those charges? Magnetic force को क्या होएगा? Magnetic force would increase because it has this velocity inside, and this velocity in this case is the velocity of the bar. So if that increases, what would happen? You have more negative charges which would appear there, and more positive charges which would appear there, and they would appear as long as you have a new electric field which would form, which would again cancel the new magnetic field force. So by controlling the velocity, you can control the charge on each end, and by that you can control the potential difference across the two ends. So if you remember, this is exactly a situation something like this. When we consider a battery, what battery had a positive terminal and a negative terminal, and we had a kind of a motor which was moving negative charges from this plate to that plate, while maintaining a certain potential difference across the two plates. That's what a battery does. So if you look at here, what you have is, you have a certain potential difference across this, and by moving you are maintaining their potential difference by moving negative charges out from positive plate towards the negative side. So exactly the same thing happens here as happens in there. So what you have is, by motion of a conductor inside a magnetic field, you have produced an EMF or electromagnetic EMF source in there. And this EMF source, this is called as motional EMF, if you might have heard the name. So you have created a certain potential difference just by moving a conductor inside a magnetic field. What if you have this negative side and you have this positive side? If you put, so let's say if you can make a closed circuit such that you put this bar on a certain conducting rail such that that conducting rail has a certain resistance to it, and you place this bar on that conducting rail. So you have this conductor, these two are conductor, and this conductor is connected by a resistor, and all of this is placed inside a magnetic field which is out of the board. So while you were moving it, what you did was created negative charges here and a positive potential on this side. And because those are conductor, those negative charges would be shared with the conductor, and the positive charges would be shared with that. So what would happen, because you have a closed circuit here, you would have a current start flowing in that circuit, and that current would be from positive to negative side in a conventional sense. So that's exactly equivalent to connecting a battery to a resistor. So now the question is, what has produced this EMF inside such a structure? So let's take this bar and take an electron inside a bar which is moving in that, initially it is moving in that direction with the velocity v bar. So you have a negative charge which is moving in that direction. True? So what would be the magnetic force on this one? The magnetic force of this charge is F magnetic in that direction, and this would be equal to the magnetic, this would be E V bar cross B, where B is out of the board. So that would be the magnitude of the force. What would happen because of that force? This electron, it would have a velocity in that direction, and there would be a certain drift velocity in that direction. So if you apply a force on a electron inside a conductor, that electron moves with a drift velocity and not with the velocity of a free particle. That's what we have already seen. And normally this drift velocity is very small, so imagine it's smaller than V bar, so I can make V bar a bit larger to represent that fact. So you have this V drift velocity. You still have a magnetic field which is applied out of the board. Now you have a charge. So initially you had a charge which was moving in that direction, so you have a magnetic force in that direction. But now you also have the charge is also moving in this direction now. So you have another velocity vector which is added to the charge, which is upward. And because you have a moving charge in this direction, you would have another force which would appear on this charge. And what would be the direction of that force? So you have velocity now in that direction, B is in that direction, so V cross B gives in this direction, but because the charge is negative, the force would be in that direction. So you would have, and because the velocity is small, that force would be a smaller force. But again, it would be a magnetic force because it is exactly coming from the magnetic field. So let me call this M1, we call this M2. What would be the direction, what would be the total magnitude of this magnetic force Fm2 which is in that direction? That would be given by E, the drift velocity, into B multiplied by N, where N is the total number of electrons which are moving as a result of that drift current. So now the question is, how we define EMF? EMF, I will run this for EMF, I think so. Okay. EMF, it is work done on a charge per unit charge. this or work per unit charge. So exactly in a battery, the work on a negative charge is done by moving it from a positive plate towards a negative plate. So that work divided by the charge, it gives you the EMF. The question in this case is, who is doing the work? Is it the magnetic field? Is the magnetic field doing work? Let's see. So if you consider this path, you have created a velocity in that direction by applying a magnetic force in that direction. True? Okay. But what about this force? So what you have is the particle is moving in that direction, the force is in the same direction, so you would have a positive work along that direction. So let's take work along one, that is a positive work, because the force is in the same direction, the movement is in the same direction. What about this force? The particle is moving in this direction, but the force is in the opposite direction. What would be the work done by part number 2? Would it be positive or would it be negative? It would be a negative work. Because as a whole the particle is moving in this direction, but the force on it is in the opposite direction, so you have a work which is negative in sign. Tejas? But whatever the case may be, what you look is, if you have particle which is moving in a certain field, in a certain force, how do you find work is the motion of that particle multiplied by the force applied on it. ठीक है, अब वो force किस वजह से दिया है? But that's the force multiplied by the displacement it takes. अब वो displacement, एक displacement उसकी इस direction में है because the whole bar is moving, और एक displacement उसकी उस direction में है. So those are the two displacements you have. But the forces are in this direction and in that direction. Okay? So what you have is, so you have to calculate force and displacement accordingly. So आपके पास दो displacement है, दो forces हैं, just measure them separately and you would get the total work. So you have this thing. What if you add all of the total? If you sum up the total work, what you would end up is a total work equals to 0. Yeah. Sorry? Yes? So positive and negative in terms of vector of work, it gives you if the force is in the direction of the displacement or is opposite to the direction of the displacement. It's a scalar quantity with a sign to it. And the sign will give you whether the force is enhancing the motion. The relative direction, it gives you the relative direction of the force and the displacement. So if you have to do conservation of energy, it would give you whether the kinetic energy is increasing or decreasing in that sense. So the total work done is 0. So how can you find it? So you have two velocities. You have a velocity Vd in that direction and the velocity V bar in that direction. These are the, what would be the resultant velocity? It would be, that's the resultant velocity of the electron. What are the forces you have? So you have a magnetic force which is in that direction, Fm1, and another magnetic force which is in this direction, Fm2, and the resultant would be Fm, which will be the total magnetic force. So you have the velocity here, you have the force there. What is the angle between this velocity as a force and the net force and the net velocity is 90 degrees. So the total power which the magnetic field gives to the electron is given by the total magnetic force divided by the total velocity of the electron, and because both of them are perpendicular, so the net power which the magnetic field gives to the electron is 0. The question is, where does EMF come from? Because EMF is what? EMF is work per unit charge. There is something else with this. This thing is moving in this direction, and why it is moving? Because you are applying a force on it, and that force is the external force which you are applying on this bar. And if this bar has to move with a constant velocity, it means that this external force is balanced by another force. And what is that force? This is Fm2. So let's say what is the work done by the external force. This is equal to F external dot velocity of the bar, because that would the whole bar is moving in the direction of the external force. So get it? Sorry, power at this. Give me clear. Okay. So what is F external then? If what we assumed was the velocity of the bar is constant. If the velocity of the bar is constant, it means your external force, it is equal to this Fm2. So it means your external force that your magnitude that is equal to N E V D into D, which is the total velocity. Yeah. So that would be equal to N E V D into V bar. ठीक है? Because इस डायरेक्शन में बस कितनी फोर्सेस हैं? एक तो okay, you are applying a certain force on it. लेकिन इस डायरेक्शन में velocity constant है. If the velocity is constant, it means that the forces are balanced. So we already know the force in that direction, but we are applying a force in this direction, so they should balance out. So what is N? N is the total number of electrons. So if I multiply N by the total volume, then I would get this total N. So N multiplied by volume, what is the total volume? It is the area multiplied by the length of this conductor, which is the cross-sectional area, E, VD, P, V bar. This is equal to, you have N, E, into A, L. What is this thing? That's current. So that's the current density multiplied by the area. This would be a total current ILB into V bar. That's the power which the external field is applying, or the external, and that should create the EMF. So work per unit charge, that would be equal to F external into distance L okay, let me check the thing. So, what is the EMF which is produced across this wire? That EMF is given by the work per unit charge. And what is the EMF across this wire? So you have a a force which is given by E, V bar into B divided by E. So this is equal to V bar into B. So I can write P, this is equal to IL. Of course, this is not only force but length as well. So आपके पास वर्क क्या होता है? Force multiplied by length. So you have a force in this direction which is applied across the whole total length, and that will give you the EMF. So this would be PBL. So I can write that thing as I into V bar BL, and that is equal to I into EMF. And if you have connected this to a certain resistor R, so what would be the current which would flow through it? The current would be given by E by R, so that would be equal to, or equals to I square R. So that would be the total power. So the total power which is provided by the external force, it gets consumed into the Joule heating within the resistor. So whatever power you are providing by pulling it in that direction, it goes through while in the circuit. It is lost in the circuit while the heating, when the current, while Joule heating through a resistor. So the answer to this is, the whole thing is, see, you have a motional, you have an EMF which is produced, but that EMF is produced by the external field and not produced by the magnetic field, and this EMF is called as the motional EMF. So it means that you have, if you have a magnetic field and if you move conductors across the magnetic field, it would act as a battery in itself, so you can use it to drive currents. But that's not a very useful source because you can't move things very far, otherwise then you need batteries or generators or electrical generators in which you have to move bars for very long distances, which is not very, even for small distances, linear motion is not very feasible. So what's more feasible is circular motion. So most of your generators, they are not based on linear motion, they are based on circular motion. So circular motion is something which is more useful. So let's go to circular motion EMF. To understand that, you have to understand the torque which acts on a magnetic dipole. So instead of a wire, if you have a coil which has a certain current going through it, and it is placed in a certain magnetic field, let's say a magnetic field which is perpendicular. So if you look at the cross section of this wire from this side, so you have current which is coming out, you have a magnetic, what is the magnetic moment direction? The magnetic moment would be perpendicular to this loop area, and that would be, let's say, something like this. So you have mu which is in that direction, and you have V field which is applied in that direction. And if that's the case, what you have is you have a torque which acts on the dipole moment, and that torque is given by mu cross B. That's something which we derived last time. So how do we know this? Because we know that two forces would act. One force which would act on this side and another force which would act on that side. So if this side has a certain length A and this side has a certain length B, so the forces which acts here and the force which acts on this side, the magnitude of that force is given by, if the current is I, that would be I A into G. Because mu is always, how we define mu equals to I into area. So the area is, if you want to define the mu, you have to define that. And the direction of A would be the direction of the current. So if you use your right hand rule, then the area would be the thumb direction. If the fingers are the direction of the current. So that's how you define that. So that's the force magnitude here and the force magnitude here. And that force provides a certain torque, and that torque is given by mu cross B. That's something which we derived last time. So अब direction torque की क्या होगी इस केस के अंदर? Because you have mu cross B, so you would have a torque which is outward, and a torque which is outward has a sense like this. So this side would rotate this way, and this side would rotate this way. So that's your torque in the outward direction, a motion something like this. So if this thing happens, what would this mu try to do? It would try to move in that direction. So that is mu now. Let's say it moved in that direction and you have a magnetic field in that direction. What would be the torque in that case now? It would be zero because mu and B are no parallel. But let's say it was moving in that direction, it has some inertia, and because of that inertia, it slightly moved in the other direction, so that your current was, that mu tilted slightly in that direction. So B is still in that direction. What would be the torque now? We have mu cross B, because mu is on this side, so the torque would be on the other hand side. So those arrows, they would reverse the sign. They would reverse, and this would try to tilt itself back into that direction. So if it goes that direction, it would again try to. So this is kind of the low. So if you look at the system, a system, whether it's a charge system, whether it's a current system, it always tries to go to a low energy configuration where its energy is lower. So on this side, if the torque is, if the magnetic moment in this direction, it has not low energy, so it like to go to low energy, and low energy is that one, that configuration. And similarly, if it is in this side, it's still a high energy configuration, it would try to go back to the low energy configuration. So that's the low energy configuration of the charge carriers, of the current. So you can define the energy, which would be the potential energy of this dipole, and this potential energy I can write as this is equal to minus mu dot B. You can derive it, but I'm just giving you the expression. So when mu and B are parallel, so mu dot B would have maximum value. And if it has maximum value, you would have a minus sign, which means that the total potential energy would be minimum. So that's why you have a minus sign over there, to make the total potential minimum when mu and B are parallel. So what would be the maximum potential? When mu and B are anti-parallel, when they are anti-parallel, what you would have is a negative into a negative, you would have a positive potential. And what if they are perpendicular? Is zero. Okay? So if this is U and this is the case, let's say This is the case where they are parallel. This is the case where they are perpendicular, and this would be the case where they are anti-parallel. नहीं, it's still at a higher angle, perpendicular जगह है. हाँ. हाँ. तो ऐसे रहेगा. हाँ. Yes. So what if you have, let's say आपके पास एक, that's the potential u of x, let's say x मेरे पास ये है, for a harmonic oscillator. That's what you have for a string. That's how the potential is half. Okay, x gives us a parabola along x equals to 0. So what if you have this is your mean position. Agar if you leave it at the mean position, it's already the minimum position, it would stay there. But if you displace it from the mean position, what it would try to do, it would come back, it would have a restoring force. Okay? So what was your question? Parallel, yes. Minimum value of potential. Okay. It should stay there. When mu और b आपस में parallel है, ठीक है? नहीं, so yes. Yeah, so if you leave it at that position, it would leave there. Yes. But if you move it from either side, the potential suddenly goes up. It goes up. It goes to 0, and जब आप parallel perpendicular करते हो, and जब parallel करते opposite करते हो, it goes even higher. So that's. So if you have angles, for example, अगर potential को मैं angle के execute करूँ, let's say such that theta is the angle, that's theta, and that's u of m. So what you would have is, you would have something like this. Of course it would come back. So अगर theta 0 है, you have a minus b. अगर theta 90 है, you have the potential equals to 0. अगर theta जो है 180 है आपके पास, then you have potential at higher value. I hope it answered the question. So the question is, let's say if I start with this configuration, जहाँ पे अगर b जो है upward है, but mu जो है आपके पास downward है, ठीक है? So the current is flowing in this direction, जो अगर mu जो है आपके पास downward है. And if you leave this coil, what would this coil do in the presence of that magnetic field? This coil would rotate, and would rotate until mu becomes parallel to that thing. So the next question would be, can I make this motion continuous motion, not just one motion, but rather a full continuous motion? So, and that's what electric motors are. That's how electric motor works, that they make this circular motion a continuous motion and not just one cycle or half a cycle. So how does that thing work? So what you have is a loop such that the loop is connected with a certain split rings with a certain so one side of the loop is connected to one split ring, the other side of the loop is connected to another split ring. And all of this is placed in an external magnetic field which is in that direction. So how does this split ring works? Is something like this. You have two electrodes like this which are circular, such that those electrodes have a kind of a metallic brush which is touching those, and then you have another metallic brush which is in that direction. So this one is connected to a positive terminal and this one is connected to a negative terminal. And of course this one then goes to one part of the ring, this one goes to another part of the ring. That's how the system is. So when the ring rotates, this split ring also rotates with it because this is connected to that thing and it's a rigid body, so the whole thing moves around. So if this thing moves around, let's say at this position, what you have is this side is connected to negative and this side is connected to positive. So the current which is flowing is current which is moving in that direction and coming back into that direction. So because of that, you would have a magnetic moment which would be downward just by the right hand route. But once it is rotated, this part would touch. So let's say when it rotates, then another part, the positive hand, it would touch, okay, I don't know how to draw it, but touch it, and the other part would touch the other one. So so when this thing rotates, what happens? ये कनेक्शन आपके पास चेंज नहीं हो रहे, ये कनेक्शन आपके पास है, ये चेंज होएंगे तो ये वाला फिर पॉजिटिव नेगेटिव के साथ कनेक्ट होएगा, ये वाला जो है वो फिर आपका पॉजिटिव के साथ कनेक्टेड है. जब उलट होएगा, you would have a current which would be flowing in the opposite direction. So you would have a magnetic moment now which would be in that direction. So what does it mean here in terms of that thing? So let's say you have a coil जिसके जहाँ पे मैग्नेटिक मोमेंट आपके पास इस तरह है and your magnetic field is in that direction. So what would this coil do? It will rotate until the mu becomes in that direction. But at that point, जब mu यहाँ पे आएगा, what happens कि आपके जो polarity है, it would change because of this split ring. And जब polarity change होती है, आपका mu क्या करेगा? It would again flip sides. It would again flip side because current जो है आपका rotate हो गया. So it would again rotate, and जब यहाँ पे आता है, again the polarity changes. So that's how a perpetual motor, that's how the fans work, that's how your water motor works. Because you apply a certain constant potential within a magnetic field, and because you have this constantly changing polarity, you are changing the sign of the mu, because you are changing the sign of the current or the direction of the current. Yes. Okay, yeah, that's true. So there would be no torque. Okay, this is kind of, it's not exactly perpendicular. थोड़ा सा rotate करता है, it would start rotating. So जो exact downward है, and in the case आपका magnetic field भी बिल्कुल constant है, वो वहाँ पे रहेगा. But normally situation क्या होती है practically, जो magnetic field आप create करते हो, it has a certain gradient to it. It's never इट्स नेवर कांस्टेंट, तो वो थोड़ा सा टॉर्क वहाँ से क्रिएट हो जाता है आपके। हाँ। फिर उसकी उसकी एनर्जी इट वुड बी पॉजिटिव, हाँ it would be positive, it would be high energy. So how do you see it? Because you have two kind of equilibrium. One is अगर आपको एक ये वाला इक्विलिब्रियम है, एक ये वाला इक्विलिब्रियम है। इस इक्विलिब्रियम में आप पार्टिकल को थोड़ा सा डिस्टर्ब करते हो, वो वापस उधर आता है। इसमें आप उसको डिस्टर्ब करते हो, इट गोज अवे। तो अगर उसमें वो भी एक तरह का इक्विलिब्रियम है, बट उस इक्विलिब्रियम के साथ थोड़ा सा आप उसको मूव करते हो, इट वुड ट्राई टू do the whole flip, it would try to come down. So that's kind of an equilibrium of this sort, not that sort. ये जो है थीटा इक्वल टू 0 पे है, वो थीटा इक्वल टू 180 पे है। So that's how electric motor work. That you have you control I, you change the direction of I, you change the direction of mu, and when you change the direction of mu, it again starts to rotate. And make itself parallel to it, to B. जब वो B को parallel आता है, the moment it becomes parallel to E, वो split ring rotate होता है, such thing की polarity आपकी change होती है, and this thing goes on, and the motor rotates. So that's one way of converting जो energy stored है, chemical energy stored है in a battery into electrical energy and electrical energy into mechanical motion. So that's how this cycle works. So let's try to look at the other way around. Whether we can transfer mechanical motion to electrical energy, and then maybe from electrical energy back to mechanical energy, so that we can use it. So that configuration is called as an electrical generator. So how does a generator work? Is you have a certain coil which has no current flowing initially, but this coil, it can move or it can rotate around a certain axis, either in that direction or that direction, depending on whatever the situation, and you have a constant magnetic field in which this loop of metal is placed. So what happens in a generator is some external mechanical force, it rotates the coil. So the coil doesn't rotate by itself, just like यहाँ पे, क्योंकि you are inducing a current, and that current was producing a magnetic moment, and that magnetic moment was rotating an external field. But in this case, you don't have any current to start with. What you have is a coil inside a magnetic field, and because the coil is initially not moving, there is no current. So what if you, by somehow, if you have a turbine or something like, and the turbine starts rotating, what would happen? That you have this coil, it would start a mechanical motion of its own. So this cycle would start rotating. So if the cycle starts rotating, what happens then? So let's look at this then. So if I look at this side, let's say this side is A, this side is B, and I'm looking at the B side, so there's the B side of it. You have a magnetic field which is in that direction. So this part of it, it would move with a circular motion around this, so it would have a certain velocity which would be a tangential velocity because you made it rotate. So that's the velocity of this side, and you would have another same velocity of the other side. And let's say you are rotating it with a certain omega, where omega is the circular velocity or the angular velocity, and then omega equals to d theta by dt, where d theta is this angle. So if you have a circular If you are giving it a certain circular motion, then you are changing this theta while rotating the whole coil. So if you have a certain omega, you would have a certain tangential velocity of the end of the coil. And that V would be given by, what would be the magnitude there? R omega, that would be the magnitude of that tangential velocity. And what is R in this case? If the length of this side is B, then R is B by 2. This B by 2 omega, that's the velocity. That would be the velocity of this arm, and that would be the tangential velocity of that arm which is rotating. अब velocity आपके पास इस direction में है. Magnetic field, if I bring the magnetic field vector here, what would be the force on the electrons inside this part of the wire, जो कि यहाँ पे है. So that part of the wire is here. Which direction would the force be? So you would have V cross B give you into the board, but because it's an okay, if you are taking conventional current, that would be the direction of the current as well. So you would have a current which would be into the board in this coil. So you would have a current which you would have into the board would be that direction. Similarly for this, you would have a current which is coming out of the board. That would be a current which would be in this direction. And how does this current generated? This current generated because of the circular motion itself. So a current element was moving within the magnetic field, and that created a certain force which created currents. What about these two sides? These two sides are also rotating. Anyway, you force लगेगा, वो भी इसी direction में लगेगा. But what happens in those cases, that normally a positive charge appear on this side and a negative charge appear on that side, but you don't have a net flow sort of say. So you have a positive and a negative on either side of the wire, but no current as such along the wire, because the force is perpendicular to the wire itself. But anyway, you have current, so there is a force, so you have a current which is generated because of circular motion here, and a current here, so you would have a full current which would flow through a circuit. Let's say you can connect it into a certain resistor, and you would have a current which would be flowing through it, such that there would be a certain power which would be dissipated across the resistor. So what you have is, by rotating the coil, you have created an EMF source here as well. Because the current starts flowing, it means that you have created a potential inside a wire, so the current can flow through that potential and start flowing. So the question now would be, what would be the EMF in this case? Question here or? What would be the force? Okay, let me. So let's look at the EMF you create in this case. So imagine, so let's start with the configuration, जिसमें आपके पास current जो है इस side में into the board है, and then you have this side V, and then you have a current which is coming out of the board, that's into the board, that's out of the board, and this circle length is B, and this thing is moving with a certain, so we are rotating this whole thing around this axis. Okay. You have a magnetic field applied in that direction. So if you don't rotate it and you have a current flowing, what would be would there be forces on this current? due to that magnetic field. There would be forces. So you have this current rotating, and those current rotate. So when you start to rotate, you have current start flowing. And once current start flowing, the magnetic field would start acting on those currents as well, because the magnetic field can apply force on current such that those forces are given by L cross B, where L in this case is the length of this wire. So if you have to keep them rotating, you have to work against this force to keep it rotating. So how much work you need to do, that's something we're going to find now. Because that would end up as your eventual EMF of the source. Okay, what would be the direction of that force which would act on this current due to the magnetic field? So you have the current in that direction, the B field is in that direction. Because you are taking conventional current, so you have I cross B, that would give you a force which would be in that direction, and that would be the magnetic force on the wire. What about this case? You would have V cross B, you would have a force which is in this direction. But you want to keep on rotating this whole coil in that direction, so it's continuously moving. So what you have to do, you have to apply a force which negates this torque and create a torque in the other direction. So what you do is you apply a force. So the force which you are applying by removing the frame is a force which is in that direction. That is the external force. And what would be that external force? It would have, so let's say if this angle is theta, that angle would be theta. So इस component, इस force का ये वाला component जो है, that would be what? That would be Fm sin theta component. So you have to at least apply a force in this direction equal to Fm sin theta, which the magnetic field is applying on the current element. Okay? Only then you would be able to rotate it in that direction, in this direction. So what? And similarly in this case, you would have, and what is Fm? Fm is equal to the current multiplied by L length, and the length was A, multiplied by B, and that's what your magnetic force would be. True? Okay. Okay, one thing I would like to do is, this magnetic force I will represent in terms of velocity and not in terms of current. So if you have current in this direction, you would have velocity in the same direction. So you would have E VB sin theta where sin theta would be 90, because V is in this direction and V is in that direction, so both are perpendicular. So अब external force जो है आपके पास क्या है? The external force would be equal to EVB sine theta, this should be the external force, this should be the minimum external force which you need to apply a certain. So what would be the EMF in this case? This would be the external force multiplied by the length, और length आपका क्या है इस केस के अंदर? That would be the length A divided by E. That is the work per unit charge. Is it? That's the EMF you have. Let me क्या चीज? क्योंकि क्या चीज? AC से multiply करा because EMF acts across the whole length of the wire है. So जो आपका EMF है that would be equal to क्या है आपके पास? VBAV A sin theta. अब V आपके पास क्या है? V is B by 2 omega, so this would be equal to AB by 2 omega B sin theta, and I multiplied by 2 because I have a current through this wire and a current to this wire. So EMF यहाँ पे भी produce हो रहा है, EMF यहाँ पे भी produce हो रहा है. So you have to multiply a 2 here. So the 2 cancels out, and what you have is AB multiplied by omega multiplied by beta multiplied by sine, and what is omega? This is d theta by dt. You can write d theta equals to omega dt, and if you integrate it from 0 to t or from 0 to theta, you have theta equals to omega t. So theta equals to omega t, you can replace it by omega t. That would be the EMF which you would be creating inside this wire. Where omega is something which you determine, how fast you have to move it around. The more you move it, the faster you move it, the higher will be the EMF which you are producing inside that wire. Another important thing is the EMF आप create कर रहे हो, it's not a constant EMF in time, it is a sinusoidal EMF which you create in this way. तो जो current की direction है, because of that EMF, it would oscillate back and forth in different directions. So let's say frequency, the frequency with which you are rotating is 60 Hertz, which means that you are giving it 60 revolutions per second. Let's say a certain generator is rotating it by 60 revolutions per second. Then omega is given by 2 pi into f radians per second. That would be the omega which goes into there, and that would be the EMF which you would have. You can simply also prove that let's say अगर इसी EMF को the EMF which you are providing here by rotating it, it is the same energy which you lose here in the resistance per unit time, so that the energy which you give by rotating it, it is consumed by the resistor. So the resistor, it has to get energy from somewhere, and that energy is provided by the rotational motion which an external force is giving this. So that's how a generator works, and that's how your AC circuit, they get their power from such a source of EMF. Any question? Yes. Yes.